Bismillah ar-Rahman ar-Rahim. Molecular modeling using electronic structure method. Uh, to go through molecular modeling, we have to have some basis concepts. First, we speak about electronic structure method, which is based on the basis of Schrödinger wave equation. But practically, the exact solution of Schrödinger equation is not enough, so that it has several approximations to its solution. According to this concept, it has the following classes. The first one is semi-empirical method. Semi-empirical methods use parameters that are derived from experimental data to simplify the computation. This class is inexpensive, which means that it consumes less time and provides researchers with a reasonable quantitative description of the molecular system. Moreover, it provides fairly accurate quantitative prediction of energies and structures for systems where good parameter set exist. Second one is ab initio. This class is based only on quantum mechanics. It provides high quality quantitative predictions for a broad range of systems. The third one is density functional methods. This class is similar to ab initio in many ways. It requires about the same amount of computation resources as Hartree-Fock theory, which is the least expensive ab initio method. It provides accurate results more than ab initio. So the density functional theory, which is termed DFT, become a popular class of electronic structure method. A DFT method is accurate and attracts many researchers because they include the effect of electron correlation in their models. It is concerned with modeling the properties of atomic and molecular systems such as energies, structures, and vibrational spectra, interatomic bond distance, and bond angles, which can be predicted using DFT to within 0.05 angstrom and up to 2 degrees, respectively. Bond energies are estimated accurately to be within 5 kilocalorie per mole. Another very important consideration when using modeling calculation are the use of suitable basis set. A basis set is defined as the mathematical representation of the orbitals. The combination between a theoretical procedure like DFT, for example, and the basis set is called a model. Each model is used to approximate a solution for Schrödinger wave equation. Through this solution, a physical parameter can be obtained. One of the most important parameters, which is obtained through the first derivative, is the optimized geometry of the given molecular structure. It is considered as being the measure of asymmetry in the charge distribution. In addition, the second derivative gives some parameters such as vibration frequency and polarizability. The vibration frequency depends on the second derivative of energy with respect to the nuclear position. The accurate prediction of vibrational spectra is the most demanding test of DFT calculations. So the polarizability is also depending on the second derivative of energy with respect to an electric field. It is considered as being the measure of asymmetry in the charge distribution. I know this terminology is a little bit complicated, but it's the basis of this work, and we will go through to learn how can we use these parameters to make a model molecule and make calculations and so on, through the examples, of course. The second derivative also gives some parameters such as vibration frequency, polarizability, and also the accurate prediction of vibrational spectra is the most demanding test of the DFT calculations. Now let us start again. How can one solve this equation with quantum mechanics? Let's have a look to the wonderful equation of Schrödinger, which is a second order equation. This quantum mechanics describes the energy of a molecule in terms of interaction among nuclei and electrons, which is given by the famous equation of Schrödinger. Actually, the electrons try to maximize their attractive force, as indicated in the figure, force with the nucleus, and minimize the repulsive interactions with each other. They do this by creating no-fly zone. That's no other electrons can enter the electrons interaction are then correlated. This is the main concept to go from the Schrodinger wave equation for the atom and Schrodinger wave equation for the molecules. And then let's say that, as mentioned, a method which make a partition of the electronic energy in several terms was developed. As we compare here, this is the equation of Schrodinger, which is two terms, but if you describe the equation for the molecules, we have four terms instead of two terms. It's the first one is AT is the kinetic energy term, EV is the potential energy, and the other one is for the nuclear electron attraction and of the repulsion between pairs of nuclei. AJ is the electron repulsion term, and EXC is the exchange correlation term and contains the remaining part of the electron interaction. Seems to be that you describe this equation, you got some important parameters through the solution of this equation, and then we can predict some important parameters of molecules. If I'm not a physicist or I'm not working in mathematics, I can go through this work through the applications. That's why we have a few applications as the first job for my molecular modeling. Some of our colleagues will describe their model molecules. How can they build the model molecules, and then how can we make the calculation? Thank you very much.